So good morning, everyone. Welcome to today's lecture recap. And so we've been talking about oscillations. Last class, we were kind of focused on this mathematical description of simple harmonic motion. So understanding the various parameters that appear in the cosine function and how those are related to various aspects of the motion, and understanding the relation between the position and the velocity and the acceleration. And today what we're going to do is take a little bit more of a physical approach and answer some questions, starting with some particular physical situations. We're going to try to understand, how do we predict, number one, the equilibrium position that a system will take? Number two, how do we predict the amplitude of an oscillation given some particular initial conditions? And number three, we're going to talk about predicting the oscillation frequency in some sort of relatively complicated situation where there are a number of different forces acting. Okay. So let's get started with this question. And so it's basically a situation where you have a spring, there's a mass on a spring, and now we add another mass onto the spring, and we want to know, how much does the equilibrium position change? So pause the video, think through that for a little while, and then we'll discuss the answer. Okay, so let's talk about this one. So I think the tricky part of this question is that we don't really know what the unstretched length of the spring is. So we know that there's some situation where we have a mass on the spring. We're then adding more mass to the spring. So we have the 1 kilogram, we add another 1 kilogram. And then we're wanting to find, how much does this change? But then there was a third situation we could imagine where there's no mass on the spring. And the formula that we have for understanding how much the spring is stretched, that basically refers to comparing the stretching or compression to the unstretched length. So let's call this L0. So when we have this formula, F spring equals minus K times X. So in this case, when we're talking about a spring, the X is really equal to the length minus the unstretched length. Okay, and so in this problem, it's a little bit tricky maybe at first, because we don't really know what the unstretched length is. But what we can do is just compare these two situations. And so what we know in each situation is that because we're in equilibrium here and because we're in equilibrium here, then the net force on the mass is going to be equal to 0. And so in the situation number one, what we can say is that mg, which is the downward force due to gravity, is going to be equal to K times x1, where x1 is going to be equal to, I'll just define that to be this positive distance between the unstretched spring, the top of the unstretched spring, and the top of the spring in this situation. Okay. So we don't really know what L0 is, we don't really know what x1 is, but we can say that in this equilibrium position here, that mg, the downward force on this mass, is equal to kx1, which is the upward force due to the spring. And similarly, so actually I should call this m1g, where m1 is the 1 kilogram. Similarly, if I call this m2, we can say that in the second situation where we're also at equilibrium, then the downward force due to gravity, which is m2g, is equal to k times x2, where x2 is the total stretching, the total compression. So x2 is the distance between the unstretched length and this compressed length here. Okay. Now in our question, what we're asked to predict is delta x, which is x2 minus x1. And so what we can see is that by combining these two equations, more specifically by subtracting equation 1 from equation 2, what we see is that we get an equation m2 minus m1 times g is equal to k x2 minus x1. And so now we're able to solve. So we get that 1 kilogram times g is equal to our k, which is 1,000 newtons per meter, times this delta x that we're trying to find. And so solving that, we would end up getting, let's get a little bit more space. So 1 kilogram times roughly 10. So that would be 10 over 1,000. So 0.01 meters, or 1 centimeter. Okay, and so the answer for that one is A. So basically, that was sort of a very careful analysis of this problem. In the end, what we can remember is that the additional stretching of the spring is going to be given by a formula which is just the same as the original formula. So we basically derived the formula in the end that delta m times g would be equal to k times delta x. So it's almost like figuring out how much extra stretching there will be if you add an extra mass. It's the same as if you didn't have any stretching at all and you put the mass on and you wanted to calculate how much the spring stretches, or I should be saying compression here. Okay, so let's consider the next question. And in this question, we don't have any mass originally. So maybe I can show this example here. Or actually, let's pretend we don't have a mass. I've got a smaller mass here. Okay, so in this case, we can imagine there's no mass originally on the spring. And then what we do is we have a mass, and then we're going to put it on. Okay. And I can do it very carefully. But what we see is that as soon as I put that mass on, then the system starts oscillating. Okay. And so in this question, we're asked to predict what is going to be the amplitude of that oscillation. Okay, so take a minute to think about that. Okay, and see if you can work it out. All right, so let's do this one. Okay, sorry, there's actually a discrepancy between the text of this question and the picture. The picture says k equals 50 newtons per meter. So we're going to go with that value for k instead of the 20 newtons per meter in the question. So we have this unstretched spring, and then we add the mass. And so what we want to do is think about, well, what does the resulting oscillation look like? So adding the mass means that we're going to now have a net downward force. So because the spring is initially unstretched, then originally the downward force is going to be just due to the force of gravity. So that's mg. And so we're going to have an oscillation that starts. And so the oscillation will take the spring downward. Eventually we'll get to some equilibrium position. And then we'll go past that equilibrium position because of the acceleration. We have now some downward velocity when we hit the equilibrium position. So we're going to keep going past the equilibrium position. Okay, so I'll draw that here. We're going to keep going past the equilibrium position. And then eventually we'll get to the bottom of the oscillation. At that point, the force from the spring is going to be greater than the force of gravity. And so we'll start oscillating back upwards. Okay. And so that's the picture of this oscillation in terms of our mathematical function. So that will be our usual cosine. And what is that the initial situation, that's where we have zero velocity and a downward force or a downward acceleration. So that's going to correspond to the peak of our cosine graph. All right, and now what does our question ask? We're wanting to know the amplitude. And so that is the distance here between the peak and the middle of the oscillation. But we remember that the middle of the oscillation, this is the equilibrium position. We oscillate about the equilibrium position. And so when we want to find the amplitude, we're basically just wanting to find what is the distance between that initial configuration with the unstretched spring and the equilibrium position. Okay, that will be the answer for our amplitude. And so then the question actually reduces to almost the same question that we just asked, even simpler. So really all we need to do is figure out how much does the spring stretch when you're in equilibrium. And so that will be just coming from setting F net equals to 0. And so that says that the K times the, I'll call this X, actually let's call it A. So we have K times A, because A is the amplitude. It's also how much the spring is stretched at the equilibrium position. And that should equal to mg if the net force is 0. And so we find that A equals mg divided by K. And then plugging in the numbers. So let's do that. Oh, well, here's some choices for you. Plugging in the numbers, what we end up is 1 Newton over 50 newtons per meter. And that works out to 2 centimeters. Okay, so the answer, if you use that 50 newtons per meter, is going to be B here. If you'd used the 20 newtons per meter, then the answer would have been E, 5 centimeters. All right. Okay, so now we're going to move on to a more complicated example. Let me introduce the example first. And it's actually very similar to the example that we had in the very first lecture on oscillations, where you have a piston and there's a gas in a piston, and we have now various forces on this piston, and we want to figure out the oscillation frequency. So this is actually a practical system that can be used in various kinds of physics experiments when we want to isolate our experiment from any vibrations that might be present in the room, from cars driving by or people walking down the hall. So what you do is you have this heavy table, you put your experiment on the table, and the table is attached to a piston, which is inside a cylinder of gas. You can see that down at the bottom here. Okay. And so now if the floor has some vibrations, they're not directly transmitted to the table. Okay, so if the floor vibrates, then maybe that will produce some slight differences in pressure of the gas, and maybe that will eventually transmitted slightly to the table, but any oscillations will be significantly reduced relative to what they would be if the table were just sitting on the floor. Okay, and so if you're doing an experiment like this, so maybe you're taking some data, you're measuring something as a function of time, for example, then you want to know everything you can about your experimental setup. And in particular, you want to know if there's some particular frequency of vibrations that you should expect from this situation, okay? Because then if you take some data and then you notice that your data has a certain periodic behavior with a certain frequency, well, you want to make sure that to understand whether that periodic behavior is because of the thing you're trying to measure, is related to the physics of the thing you're trying to measure, or is it just because your table is oscillating? Okay, and so in that situation, you would really want to know what is the oscillation frequency, what is the natural oscillation frequency for this setup. And so now I'll just we're going to calculate that for this example, but let me review the basic method here. And so if you remember, we said that our first step in understanding this is to think about the net force on your object as a function of the position. In this case, it's going to be as a function of the height of the table. And if you plot that net force as a function of height, if you're in a situation where you have a mechanical equilibrium, then that will look like this. If you have a positive displacement, so if you displace it up, then you should get a downward force. If you displace it down, you should get an upward force. And so that's what this graph is showing. And so what we said was that if we want to think about the equilibrium position, well, that will be determined by the place where the net force is 0. Okay, so that's this point here. And then if you want to understand the oscillations about the equilibrium position, for small deviations about the equilibrium position, you want to just imagine zooming in to that point on the graph where nearby then it just looks like a straight line. Okay, and the important parameter that you want to extract is the slope of that line, because that is what tells you this constant k that appears in Hooke's law. Okay, so minus k is the slope, and in terms of our function f of the position, that's just the derivative. And so what we're going to do is we're going to take the derivative of our f net at the equilibrium position. The slope, or the magnitude of that, will be the slope, and that's what you plug into our formula omega. Omega equals square root k over m. Okay, so that is our basic process. We're going to work through it in this question. There's another example in tutorial, and there'll be another example in homework. This is probably the most complicated kind of question to see with regard to oscillations. All right, so let's work through this. Again, definitely the video and try to work through it on your own. And I'm going to take this in a few different steps here. So your first step is to identify the forces on your object. So in this case, I've simplified the diagram a little bit. So we have this object of mass m, which is 200 kilograms. We want to figure out what are the forces on that object. And number two, how do they depend on this height? So eventually we want to write the net force, the net upward force, as a function of the height of the piston. Okay. All right, so let's go through this. And so in this situation, there are three forces that we need to consider. The first one is, so let's define upward forces to be positive. So our first force is gravity, and that's equal to minus mg. So all of these will be in the upward direction. That doesn't depend on the height. Second force is another downward force coming from the outside air. And that is also in the downward direction. It also doesn't depend on the height of the piston. It's just the air pressure outside times the area of the piston. And then the third force is coming from the pressure of the gas inside. So I'll call that, let's call it F gas. And so that's an upward force, and it's equal to the pressure of the inside gas times the area. So far, none of these things appear to depend on H explicitly. But what we realize is that that inside pressure, it will depend on exactly what the location of the piston is. So if I move the piston down, that gas is going to get compressed. If I move it up, it'll be less dense and have a lower pressure. So what we can do is now understand how that inside pressure will depend on the height of the piston. And if you go back to the specification of the question, we're assuming that any motion of the piston is slow, so compression or expansion is isothermal. And so then we can basically just use our ideal gas law with a fixed temperature here, fixed number of moles, and we can use the fact that the volume is related to this height by V equals H times A. And so combining these two, what we find is that P inside is nRT divided by, well, let me write P times A because that's what we wanted there. So A times P equals nRT over H. So that's just rearranging the ideal gas law and substituting in V equals H times A. And so now we're ready to write the net force as a function of the height H. And so that's minus mg minus P0A and then plus nRT over H. And we can go ahead and plug in the numbers here that are given in the question. Okay, so I actually do this on the next slide. And it works out that we get minus 5,000 newtons once we combine those first two terms. That's a constant. And then plus 1,500 joules over H. Okay, so that's the first step. This is usually the hardest step of the problem, just figuring out what are all the forces and how do they depend on the location of the piston. Next question, why don't we, just to make sure that everything is lining up with what we expected, let's graph this function. Just a rough sketch, graph the net force as a function of H and see what it looks like. Okay, so take a minute to do that yourself, and I'll do it now for you here. So let's just show that. So we have, here's our force function. There we go. So let's actually notice that the only interesting dependence here is this 1,500 over H. And so like the F versus H, the second term is just like a 1 over X function. 1 over X function looks like this. And so similarly, the term 1,500 over H is going to be a function that looks like this. But then we're going to take that and add minus 5,000. And so that shifts the entire graph downward. And so our final function is like that same shape, but it's going to be shifted downward. And so we've got a vertical asymptote at H equals 0. And we've got a horizontal asymptote at minus 5,000 newtons. So this is F net versus H. Okay, and so this is what we expected. So characteristic of restoring forces, we expect this decreasing function that goes through F equals 0. And now we're ready to extract the physical information from this. And so the first thing we're going to want to do is figure out the equilibrium position. That's the place where the graph goes through 0. And then we're going to want to figure out the K value for this, which is the magnitude of this slope. Okay, so again, looking at the graph in the vicinity of 0 there, it's like a downward sloping line, and K is going to be the slope of that. Okay, so let me get a fresh piece of paper, and then we're going to complete our question by doing these two parts. So again, pause the video and see if you can get these two parts on your own. And now I'm going to go through them. Okay, so I'll start by writing our net force again. So that is minus 5,000 Newton, and then plus 1,500 joules over H. And so to find H equilibrium, we're going to use that F net at H equilibrium is equal to 0. So that's that's where the graph crosses the axis. It's just where the net force is equal to 0. And so working that out, we end up getting 1,500 over H equals 5,000 newtons. And then that means that H equals 1,500 joules over 5,000 newtons. And these are all SI units. So we know that the final thing is going to be in meters. So that gives us H equals 0.3 meters as our equilibrium position. Next, we want to figure out this constant K that appears in the formula for frequency. And we understood that that is the magnitude of the slope. So we can either say it's the derivative of our net force function evaluated at the equilibrium position, or equivalently, it's just the absolute value. So it's negative, the derivative, or negative. Because this derivative is negative, we could also say it's just the absolute value of the derivative of f. And so we go back to our function f, we take the derivative, and so f prime of h is equal to minus 1,500 joules over h squared. Okay, and now we plug in, so the absolute value of f at h equilibrium is then equal to 1,500 joules over 0.3 meters squared. Okay, and then, so I've got the numbers here. So that works out to this 1.67 times 10 to the 4 newtons per meter. And now we plug that into our formula for omega. Okay, so the angular frequency here is square root of k over m. This is the k that we use, and then m is given to us as 200 kilograms. And when you work that all out, you end up with omega equals 9.1 inverse seconds. But usually, so that's not exactly what we normally call the frequency. The regular frequency, which is the inverse of the period, is related to omega by taking omega divided by 2 pi. Okay, and so when you work that out, you get 1.45 inverse seconds. And so basically what that means is if you have that table on the air leg and maybe you put something down on the table, then what you expect is like temporarily you get this up and down oscillation, and the frequency of that is like up and down once every 1.45 seconds. Okay, so that's what we've learned. That's what you should expect from that apparatus. Okay, so that's all for today. Next time, we're going to talk about energy in the context of simple harmonic motion, and then we'll also get into talking about the way that energy is dissipated, how sometimes energy from the oscillation goes into heat, and then you end up getting damping, which means that the amplitude of the oscillation slowly decreases to 0.